This is section 3.7, part 1, and we'll be looking at inverse functions. We'll first define an inverse function. So let f be a one-to-one function. Then f inverse equals g is the inverse function of f if f composed with g of x is equal to x for every x in the domain of g, and g composed with f of x is also equal to x for every x in the domain of f. This is an algebraic method to verify inverses. We'll have another method where we look at the graph to make sure that the functions are symmetric about the line y equal to x, and we'll be going through that. But this is the algebraic method. Okay, so let functions f and g be defined by f of x equals x cubed minus 1, and g of x equals the cube root of x minus x plus 1. We want to see if these are inverses of each other. So the first thing we're going to do is check f composed with g of x. See what we get. Well, we know that that's f of g of x, and that's f of, and g of x is equal to the cube root of x plus 1. So we're going to go into the f function, and everywhere there is an x, we're going to put the cube root of x plus 1. So the cube root of x plus 1 is our x value, and it's cubed minus 1. Well, the cube root cubed is just what's under that root, minus 1. And we're left with x. Check. So far, so good. Now, let's compose the function g with f. That's equal to g of f of x. That's equal to g of x cubed minus 1. We're going to go into the g function, and everywhere there's an x, we're going to put an x cubed minus 1. So, we're going to write the cube root of x cubed minus 1, and we can't forget about that plus 1. This is our x. Okay, and then we have our plus 1. Well, that's just equal to the cube root of x cubed, which is equal to x. Check. Therefore, g is the inverse of f. And likewise, f is the inverse of g. They are inverses of each other. Okay. So algebraically, that's how you can show that two functions are inverses of each other. Okay? And this is for the verification, not finding the inverse. Okay, let's go to the domain and range of inverse functions. This is really nice because inverse functions interchange their domains and ranges. Domain, how about I just put domain, singular, and range. And this is written out nicely here. The range of a function is the domain of the inverse function, and the domain of a function f is the range of the inverse function f inverse. Let's talk about this notation here. F inverse of x is not equal to the reciprocal of f of x. Okay? This is just a notation. almost looks like a power, but it really is a superscript of -1, okay? This means F inverse, okay? It is not the reciprocal. Just want to make sure we point that out. Okay. So functions only have inverses if they are 1-to-1. Oh, wait, I missed this. For each ordered pair AB of the function f, the ordered pair BA is in the function f inverse of x. As I said, they interchange. Functions and their inverses interchange the domain and range. So, question. Functions only have inverses if they are 1-to-1. That is correct. Why do you think that is? Well, the condition that f is 1-to-1 is essential. And the reason is, otherwise, f inverse will not define a function. And let me show you. Let's say we have f of x, and here is just some points. 2, 3, 5, 3, I don't know, 7, 9. Just made a few up. So if we went to write f inverse of x, we would, and by the way, this is a function. There are no repeated x values. So it's definitely a function, represents, that relation represents a function. But now f inverse, when we interchange the x and y values, what do you notice? This is no longer a function. This has a repeated x value. Of course, we have the same x value with two different y values. That's really what we mean. Therefore, it's not a function. So this condition that f is 1-to-1 is essential because when f and f inverse interchange their domain and range, we no longer have a function. Okay, let's find the inverse of each function that is 1-to-1. So let's first check for the condition of 1-to-1. Okay, so -2, -1, 0, 1, 2. Okay, so we do not have any repeated x values, so we definitely have a function. However, and they told us that in the beginning for each function, so we better not have any repeated x values. But look at this. 2 of our coordinates, actually 2 more, have repeated y values. So this f is not 1-to-1. Therefore, f inverse does not exist. And I think that's pretty powerful. If a function is not 1-to-1, an inverse function doesn't even exist. Let's go ahead and take a look. Since we were already told it's a function, let's look for repeated y values, and I don't see any. So g is a 1-to-1 function. So now let's go ahead and find g inverse. Okay, and you can put an equal sign, or this time I guess I'll just use set notation. So 1, 3, 2, 0, 3, 2, and 0, 4. So there is g inverse. Just interchanging the x and the y values. Interchange the domain and the range. Okay? Okay, let's go to 3.7. The graphs of 1-to-1 functions are shown. Find the domain and range of the function. Well, we can see right here we have a linear function. Our domain is all reals. Let me write that a little bit neater. And our range is also all reals. Now, we do have a 1-to-1 function. this passes the horizontal line test, which we covered before, that we had to have a one-to-one function. But now let me show you a little bit. See if I can get a dotted line here, right here. Okay. So we have this graph of the line y equal to x. Now let's first talk about this. When x is 2, y is 2. When x is 3, y is 3. All of the x and y values. When x is negative 2, y is negative 2. Okay? So the line y equal to x, all of the x and the y coordinates are the same. So just wanted to make sure you understand that. So because an inverse function and the function interchange their domain and range, they are symmetric about the line and reflect across the line y equal to x. So what I like to do is I like to maybe just put a point here for just a moment, and I'm going to work on this right-hand side. And now I'm going to just draw the mirror image of that part of the graph. I'm not going to look at this part anymore. Now I'm going to focus on this part. I don't know if that makes sense. I wish I had a little shade there. But now I'm going to focus on this part and go ahead and have a mirror image of that other part of the graph. And let me just see if I can do a little bit better job. Okay, so this is F inverse. F inverse is a reflection across the line y equal to x. Or about, or with respect. Okay, let's try another one. This is a pretty nice one. Oh, I didn't write the domain and range. So the domain of our new function f inverse is all reals as well. Okay, so let's go ahead and see if we can find that wonderful way to draw a line. Draw the line y equal to x. And we do have a one-to-one function, so an inverse does exist. Let's go ahead and write the domain. The domain of this function is 0 to infinity, and the range is 0 to infinity as well. Now, again, I usually put a little point here just for sketching purposes. I probably should have gotten rid of that point that I had drawn before, but I can't quite get rid of it. It's not on the graph. But this is how I sketch inverses. So I just work on a little piece at a time, and then I work on the other piece. And that probably should not be that flat. It should be tending up, something like that. Okay? And this is F inverse. Really don't like that. So I'm just trying to stare at this graph and draw a mirror image. Okay, I think that's nice. So that's F inverse. And again, we reflect the graph of F across the line y equal to x. Okay, now our domain and our range are also 0 to infinity. Okay, so notice that the inverse is the reflection of the original function over the line y equal to x. Now, if a function is not one-to-one, the domain may be restricted in order to make it one-to-one. For example, f of x equal to x squared, that looks like this, is not one-to-one. You can look at it right here. It fails the horizontal line test. It is not one-to-one. However, we can restrict the domain. You could take either side of it, but why not go ahead and just take that right piece? Now our function is one-to-one, and an inverse does exist. So if we restrict the domain to, what could we say? 0 to infinity. It becomes one-to-one, and the inverse can be found. So here we can say one-to-one, so F inverse exists. So restricting the domain will be very helpful. Okay, so let's take a look at this. Number 4, find a domain on which each function is one-to-one. Write the domain in interval notation. Okay, so let's go ahead and draw some axes here. And this graph is x minus 6 all squared. F of x equals x minus 6 all squared. So at x equal to 6, and you can put this in your calculator if you want to. This is the graph of, oh my, let me see if I can do it one more time. There we go. Of the graph x minus 6 all squared, and clearly this is not one-to-one. So why don't we only use this part of the graph as the domain and restrict this? So we could restrict the domain to 6 to infinity. So all of the x values that are greater than or equal to 6. Okay, and this next one, we have the absolute value function reflected across the x-axis and then shifted up 2. So it will, look something like this. So now we want to make sure we only use part of the graph that allows us to have a restricted domain that gives us a function that is one-to-one. So we decide we don't want this part of the graph, and we would like this right part of the graph. So we could have our restricted domain from 0 to infinity. Okay.